and welcome to another video in this series introducing hydrocarbon chemistry. Today we're going to be looking at cracking. Now, cracking is an important industrial process, but for this video we are simply going to be looking at the chemistry of it and how you would do it in the laboratory. Okay, before we start, you should know what the term saturated means. A hydrocarbon that contains only single bonds is said to be saturated. An example would be the alkanes. You should know what the alkanes are, and you should be able to recognise the full structural formula of an alkane. You should also know what the term unsaturated means. The alkenes are an example of unsaturated hydrocarbons. That means they contain at least one carbon-to-carbon double bond. You should also be able to spot that double bond in the full structural formula of an alkene. You should also now be aware of the test for unsaturation. If you add bromine solution to a hydrocarbon and it goes colourless, then it means the hydrocarbon is unsaturated. Okay, so let's see how we do cracking in the laboratory. We start, as we so often do, with a test tube. In this case, you want it to be a fairly large test tube. And you put some ceramic wool in the bottom. Now, the ceramic wool is absorbent but doesn't catch fire. That's about all you need to know about it. And you're going to soak a sample of a hydrocarbon into that ceramic wool. Now, you want that hydrocarbon to be made of large molecules, which means it will be gloopy, it will be thick. The technical term is it has high viscosity. Hydrocarbons with large numbers of carbon atoms have high viscosity. Okay, we're now going to mount that in a clamp and stand. I'm not going to draw that in, really can't be bothered. Okay, and we're going to put in a catalyst. And the catalyst we want is aluminium oxide. There are others you can use, but this is the most common. We'll put in a stopper and a delivery tube, and another wee test tube there. Now, into that wee test tube, we're going to put bromine solution. Right, now we're going to heat the large test tube, and what will happen initially is you'll see a kind of white vapour appearing, which resolves into little droplets of a runny hydrocarbon. Now, the fact that hydrocarbon is runny tells you it's made of smaller molecules than the one you had to start with. But more interestingly, perhaps, you'll get bubbles appearing. There's a gas produced here as well. And that gas turns the bromine solution colourless, which means the gas is unsaturated. It's probably ethene, could be propene, but it's certainly unsaturated. Now, when the reaction's finished, before you stop heating, you have to take that little test tube away. Otherwise, you get what's called suckback. The gases in the large test tube will contract, they'll get smaller as they cool down and could suck the liquid back from the wee test tube, and that could cause the large test tube to break. Okay, so what's going on next? We heated a saturated hydrocarbon. That's what we did. That saturated hydrocarbon has high viscosity. That means it's composed of large molecules. We heated it with a catalyst, which was aluminium oxide, and that produced a low viscosity hydrocarbon, which therefore is made up of smaller molecules than the ones we had to start with. We also produced a gas that decolorized bromine solution. That means that gas is unsaturated. Okay, let's see what's going on in terms of molecules here. Let's assume we crack decane. That's decane there. Single bonds only, 10 carbons, 22 hydrogens. That is an alkane. Okay, let's suppose we heat that with aluminium oxide and it breaks the molecule, like that. Now, we have a couple of problems here. You see the carbons at the ends of those two chains where it broke? Each of those has only 3 bonds. carbons need to have 4 bonds. Now we don't have any hydrogens to spare here. We can't just add hydrogens on. So what we have to do, we have to transfer a hydrogen from one to the other, like that. Now that molecule on the right is a happy molecule. All the carbons have 4 bonds, all the hydrogens have 1 bond. That is pentane, C5H12. It's a saturated hydrocarbon. But look at the molecule on the left. Those 2 carbons now, on the right hand side, they have 3 bonds only. But we've seen this before. We can form a double bond between them, like that. And again, that's now a perfectly happy molecule. Each carbon has 4 bonds. That is pentene. It is unsaturated. It's an alkene. So what is cracking? Cracking breaks hydrocarbon molecules into smaller ones. But in doing so, it always produces a mixture of saturated and unsaturated hydrocarbons, simply because you don't have enough hydrogens to make 2 saturated molecules. Okay, so what's actually produced each time? Let's take any old hydrocarbon. That formula there is the formula of any hydrocarbon, where A is the number of carbons and B is the number of hydrogens in the molecule. Now let's suppose that cracks like this. We get 2 products. Again, they will be hydrocarbons, where W and X and Y and Z are the numbers of carbons and hydrogens in the 2 product molecules. Now I know it looks all a bit algebra at the moment and a bit sort of difficult to understand, but we'll bring some sense to it. You see, the thing is, you can't magic atoms out of nowhere, and you can't magic them into non-existence. So, that number there plus that number there must equal that number there. Okay? A is the number of carbon atoms you started with, so W and Y added together must equal A. That. For exactly the same reasons, that number added to that number must equal that number. So X plus Z equals B. Okay, I think the best thing we can do is look at some actual examples. Let's take this alkane. You've not seen that one before. That's dodecane, C12H26. Notice it fits the general formula for the alkanes, CnH2n plus 2. Okay, let's suppose that cracks, and one of the products is octane, C8H18. Again, that's an alkane. It is saturated. Fits the general formula for alkanes. Okay. Now, we started with 12 carbons. So far, we've only used 8. That means the other product must contain 4 carbons. 8 plus 4 is 12. For the same reason, we started with 26 hydrogens. So far, we've used 18. That leaves us with 8 we haven't used yet. So the actual product must be C4H8. Now that is not an alkane. That fits the general formula for the alkenes. So C4H8 is unsaturated. It's butene. Okay, just another one. We'll start with decane this time. And let's suppose when decane cracks, we get propene. There it is, propene there, C3H6. Now we started with 10 carbons. So far we've only used 3. So the other product must contain 7 carbons. We started with 22 hydrogens. There are 6 in the propene. That means the other product must contain 16 hydrogens. Check the adding up, you'll see it works. So, you also get heptane. Notice you get a mixture of an alkene and an alkane again. And we can in fact do this backwards. Let's suppose we start with an unknown hydrocarbon, we crack it, and we get those two products there. That's hexane and propene. Right, we've got 6 carbons plus 3 carbons, that's 9. We've got 14 hydrogens plus 6 hydrogens, that's 20. So the original molecule must have been C9H20. And that's nonane. Okay, summing up then. Cracking breaks large hydrocarbon molecules into smaller ones. That's the definition of cracking. And it always produces a mixture of saturated and unsaturated products, simply because you don't have enough hydrogens for both products to be saturated. We do it by heating with a catalyst. Now the catalyst is usually aluminium oxide. As I said, there are others, but aluminium oxide is the most common. And finally, the total number of carbon atoms and hydrogen atoms must be unchanged. So that allows you, if you know 2 of the substances in the equation, to work out the third. Okay, that's all for now. Bye just now.